Hey guys, welcome to 5.1. This is the first lesson in Unit 5, which has to do with the rational roots theorem and the fundamental theorem of algebra. Now, that sounds really complicated, but I promise it's not as bad as it sounds. What we're going to be doing is finding roots of polynomials, what we were working with in the last chapter. And you were doing this when you were solving polynomials by factoring, using the quadratic formula. Roots are just solutions that make a polynomial equal to 0. So the rational root theorem, it's this theorem that states for any polynomial, that's what this is up here, in standard form. This is like the fancy way of doing it. This an x to the n plus all the way down to a of 0, which is just a constant. Don't worry about that. You're not going to memorize that or anything. But it's p over q, where p is the factors of the constant term, so whatever the last number that doesn't have the variable is. And then q is the factor of the leading coefficient, so whatever our a value is. It's the combination of all of those, plus or minus though, because they can be positive or negative, as we've seen with solutions in the past. So how we do this, list all of the possible roots, p over q. Identify that p is factors of the last term. So our last term here is 24. There's a lot of factors in 24. We have 1, 2, 3, because those all divide into it. 4, 5 does not divide into 24. 6 divides into 24. 7 does not. 8 does. 9 does not. 10 does not. 11. Then we get to 12. And then lastly, 24 itself. So that's 1, 2, 3, 4, 5, 6, 7, 8 different factors that go into 24. And then we want the factors of the leading coefficient, which is the first part here, 3. And the only factors of 3 are 1 and 3. Remember, factors are just numbers that we can divide in. And then it's plus or minus, because we can have positive and negative versions of all of these. So what we're going to do now is list out the different combinations. So the first thing is 1, or everything on the top divided by 1. So it's plus or minus 1 divided by 1, which is 1, 2 divided by 1, and you're going to see that it's all the same numbers as what's on the top. 3, 4, 6, 8, 12, and then 24. Now that we've used 1, now we got to go through all those numbers on the top, but now we're going to divide them by 3 instead. So we get plus or minus 1 divided by 3, we're going to leave as 1/3. And then we get to 2. 2 divided by 3 is 2/3. Now, once you get to 3, though, 3 divided by 3 is 1, and we don't need to list that because we already listed it before. Then we get to 4 over 3, so plus or minus 4 over 3. Then we get to 6 over 3, but 6 divided by 3 is 2, which we already listed up here. So we don't need to list that again. 8 divided by 3 we did not list. 12 divided by 3 would be 4, so we don't need to list that one again. And 24 divided by 3 is 8, excuse me. So that's the last one that we need to list. Excuse me. These are all the possible solutions. Rational solutions, mind you, because we can still get imaginary solutions. But these are the list of possible rational solutions that we can get, meaning basically nice numbers, nice answers. Now the fundamental theorem of algebra, this is our other theorem that's important. If a f of x is a polynomial with a degree of n, so a polynomial for a general degree of n, so some degree bigger than or at 0 or larger, then the polynomial has n number of roots. This is just what I've been trying to show you, that when we have a x cubed equation, we know there has to be 3 solutions because the highest degree tells us the number of roots, which is the same as solutions. So how many roots does it have? Let's look at these. There's 2. This is a squared, a quadratic, so there's 2 roots for this one. The highest degree is 2. This next polynomial, 5 is the highest degree, so we have 5 roots, or we know there should be 5 solutions. All right, example 2 says find all of the zeros of f of x equal to x cubed plus x squared minus x plus 15. Before, what we tried to do is factor that using factoring by grouping. We're not going to do that this time. We're going to list all of the possible rational roots, and then we're going to use a calculator to actually graph this, and then we're going to break it down using synthetic division, like what we were doing before. So to list all of the possible rational roots, we do p over q. Or did I say that wrong? Yeah, p over q. We look at 15 first. So what are the factors of 15? Plus or minus 1, 3, 5, and 15. Over the factors of 1, which would be our leading coefficient, which are just 1. So this one's much more straightforward because you only have to take 1 and divide that into everything up above. So we get plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. There's far less options than there was in the previous example. And that's going to happen a lot of the times where we have way less than, I mean, this is a ton. Now what we want to do, these are the possible roots. These aren't guaranteed solutions. We want to figure those out using our calculator. So now let me split screen with the calculator, and I'm going to show you how you type this in. All right, so now that you have the calculator up, you might need to pause this to make sure that's up. I'm using my cursor thing here to show you. We are going to click on this y equals button in the top left corner of the calculator. Oh, I should have been in the home page. So if you hit the home page and then you hit the y equals, it takes you to this. It's got y1, y2, all of those. Those are different equations that we can plug in. We are going to type in this equation here that we were using. So to get the variable, you got to find this x right here. It's underneath mode. So click x, and then we just use the buttons to fill it out. So to get a cubed, we need to hit the caret, 3, move your cursor over, plus x squared minus x, and then plus 15. Now that we have this is like y equals x cubed plus x squared minus x plus 15. We want to look at how this is on a graph. So here in the top right corner of your calculator, hit the graph button. Now we can't really see much because of this. So what we need to do actually is we are going to hit zoom. Let's go zoom fit. Okay. Now the zoom fit in this case just made it in a way that we could see kind of the curves of our polynomial. And if you look here, if we zoom in, now I'm doing the exact opposite. Why can't I zoom in? Okay, never mind. We're not going to zoom in. I'm going to go back to the graph. This doesn't have quite as many features as the usual calculator. There is a point though, right there. That's the point I was trying to get to. Oh, can we move this? Oh, that's cool. Sorry, I'm learning stuff as we're doing this. That point, as you see, is approximately negative 3, 0. I know there's like, if you look down here, you can see the x and the y. It's actually right at negative 3. I just can't be super exact because I'm moving it with my pen. So what that means is, since it goes through the x-axis at that point, and then x value is negative 3 is going to be one of the roots to this polynomial, or one of the solutions. So let's go back here, and let's look at our list of possible roots, and notice, we talked about this one earlier, negative 3 is a possible root. So what we're going to do with that is we're going to use synthetic division to break down the polynomial and help us find the other ones. So make your box negative 3, and then line up the coefficients, 1, 1, negative 1, 15, and then drop down the first one. Negative 3 times 1 is negative 3. Add those, we get negative 2. Multiply, we get positive 6, because 2 negatives. Combine those, we get 5, and then multiply the last part, and you get negative 15. Now we know that we did this right because we needed to get 0 at the end. That means our remainder is 0. Now what we can do is rewrite this as the polynomial form, which is 1 degree less than a cube, which is x squared, minus 2x plus 5. We are trying to solve, because we want to find the zeros, so we need to set this equal to 0. Let me pull back the graph here just to talk about this. Notice, if you look at the graph, it looks like it only goes through the x-axis at one point. The reason for that is because we only have one real solution. The other solutions we're going to find out are actually imaginary. And to find those solutions, since we can't factor it, we got to use the quadratic formula. So x equals negative b plus or minus the square root b squared minus 4ac all over 2a. Okay, so I'm going to do the b squared minus 4ac part first. Negative 2 squared minus 4 times 1, and then c is 5. We get 4 minus 20, which is negative 16. Now let's fill in the rest. Negative b, negative of negative 2 is positive 2, plus or minus the square root of negative 16 all over 2 times 1, which is 2. Now let's simplify this. So we get 2 plus or minus, the square root of negative 16 is going to be 4i. That's a perfect imaginary number. Now that we have that, we can simplify this even further because 2 divides into everything. So we're going to get a simple version of x equals 1 plus or minus 2i, because we can divide 2 into both of those. Now we did have one more solution though. Thinking about the fundamental theorem of algebra, we started with a cube. 3 was the degree, so we should have 3 solutions. The third solution is what we use to break it down, this negative 3. So that's the other solution. All right, let's go ahead and try some more here. I'm going to do 2 more with you, and then I'm going to let you guys try the last one. So let's use the graph to shorten the list of all possible rational roots. Okay, so if we were doing the rational root, p over q, I got to make sure that we practice this. Factors of the last term are just 1 and 5. Excuse me. And then factors of the first term of the leading coefficient are just 1 and 2. But now we need to list out the different possibilities. So let's start with taking the top numbers divided by 1. So plus or minus 1, plus or minus 5. And then we take the top term divided by these. Plus or minus 1/2, plus or minus 5/2. So if we use the graph now, let's pull that graph back up. Let's hit the y equals. We're going to clear this out. We're done with that graph. Let's type in this equation. 2x cubed, and you'll get better at with time typing this in, minus 5x squared minus 2x plus 5. If you need to pause and type that out and practice it, that's fine. Okay, then we hit graph. And now we want to hit zoom. Let's hit zoom fit and see if that works. No, we might have to hit zoom standard for this one. Yeah, zoom standard is what's going to be what we're usually going to use, because that gives us a 10 by 10, which is a typical coordinate grid. Now this one, this is pretty nice because we can see the 3 solutions. I really like that you can mark this. So if you move that cursor, why isn't it letting me do it this time? Okay, well, as we get closer and closer, we have 3 points that go through the x-axis. There we go. Finally got it. Our x value here is -1. And if you look back at the list, that's one of the possible roots. Okay, so there's one solution. So we know it's going to go right through -1. Another solution is right here at +1. And then the last one, this is the fraction part. So this one, it's harder to see. But if you think about our list of fractions, we have 1/2 and 5/2. Well, 5 divided by 2 is 2.5, and that's exactly what this point looks to be. So if we click on it here, come on. It's just a, yeah, It says 2.525, but we know it's a little bit shorter than that. So 2.5 is our other answer. And we could actually do this one without using synthetic division. The reason we had to use synthetic division for this one up here is because we got imaginary solutions. We needed to break it down in order to use the quadratic formula. All right, so I'm going to do one more here, and then I'm going to let you guys try this. So find all solutions to f of x equals x to the fourth minus 3x cubed plus 6x squared minus 2x minus 12. First thing we want to do here is, if it says to list out the possible solutions, we should do that. I'm going to do it here just so we get in that practice. So p over q plus or minus 1 plus or minus 2. Remember, we're looking at the last term. Plus or minus 3 plus or minus 4 plus or minus 6 and plus or minus 12 are all the factors. And then we just have 1 here. So I'm not even going to waste your time. That's what I would end up doing, because 1 is the only factor of 1, so those are all the possible rational roots. So let's go ahead and type this in to our calculator, get this graphed, clear it out. We want to do x to the fourth this time is our first term, minus 3x to the third plus 6x squared minus 2x minus 12. Okay, do a quick little double check, make sure I got that typed out right, and then we hit graph. Okay, if we hit zoom fit, I just kind of want to see what this looks like. Yeah, that doesn't help us. So go back to the zoom standard, at number 3. All right. I'm going to have to learn how to use this graph a little bit more. I'm so used to using the other graphing calculator, so I apologize. But we do notice 2 points right away. That point there is -1, and this point here is +2, which means those are 2, and those are a part of our possible solutions. If we go back here, 2 and -1 are both options. So what we're going to use is those roots to break down the equation until we can get it into something that will factor, or we can use the quadratic formula for. So list out the coefficients. 1, -3, 6, -2, and -12. Do the process that we love. Multiply 2, add -1, multiply -2, add, we get 4. 2 times 4 is 8. Add those, we get 6. And 2 times 6 is 12. We always want to get 0 at the end if we're doing this correctly, because we need to break it down. Now the thing to be careful about here is we started with a 4th degree, so we should have 4 solutions. But that means that this first term is going to be x cubed, because it's 1 less. Then it's minus x squared plus 4x plus 6. This cube we can't factor yet. We need to get it down to a quadratic. That's going to be the easiest way. So let's do the exact same thing by using the coefficients, which we already have lined up. But let's use the other rational root. We already said that 2 is a solution. And then the other one that we talked about was over here on the graph. If it's going to let me, oh, I had it. There it is, -1. That's the other point we're going to use. So you can actually use synthetic division on the same polynomial more than once. Bring down the first term, we get 1, multiply those, we get -1. Add those, we get -2. Multiply, we get +2, 2 negatives. Add those, we get 6. -1 times 6 is -6. And just like the one before, we get 0. So now we broke that down. That was a cubic that we broke down. And now we have it down to a quadratic of x squared minus 2x plus 6 equals 0. So now that we have it down to the quadratic, we have 2 solutions that we've listed out, 2 and -1. We need to figure out the other 2 solutions using the quadratic formula, of course. We're going to use the quadratic formula a lot, so please get used to that. -b plus or minus square root b squared minus 4ac all over 2a. In this case, x equals the opposite of negative b, which is 2, plus or minus the square root of b squared. So negative 2 squared is 4, minus 4 times 1 times 6. I'm just skipping the discriminant part. You can do that separately. X equals 2 plus or minus, this part here is going to be 24, and 4 minus 24 is negative 20. And then we got to break that down. 4 and 5, and 4 breaks into 2 and 2. And it's negative, so we need to pull an I out. So we get 2 plus or minus, we have one pair, so 2i, and we have the square root of 5 left inside, all over 2. And then that's going to break down because we can take a 2 out of all of those. And the final answer we get here is 1 plus or minus I square root of 5. And we have two solutions over here, two solutions over here, which makes sense since we started with a quartic. Okay, this is a really long video. I apologize for that. Do the best that you can and try this example 5. What you're going to do is find all the possible roots, so list them out like we did before, and then use your graphing calculator to figure out what they need to be and break it down if need be.